Well, hi there and welcome to this ISOP webinar. My name is Mike Smith. I'm a pharmacometrician here at Pfizer in Sandwich in the UK. And for the last 5 years, the majority of my work has been working on DDMore project. And so today's webinar is to give you an introduction to DDMore and to try and show you some of the tools and the products that we've developed in those 5 years. So the basis for DDMore is that we have the kind of current state of play is that we have limited access to modeling knowledge. So people perform work, they build models, and they may be published, but it's difficult to share models between analysts. We have non-compatible software languages, meaning that we encode the model in one language, but if we want to pass it off to another piece of software to do some work with it, then we have to rewrite the model in that software language to pass it off. And this causes a huge amount of wheel spin and waste of time and resources as people repeat work, rebuild models, reanalyze data, and recode models from one software tool into another. And so DDMore was set up to try to resolve these issues and address these issues in a number of ways that we'll look at in a minute. A bit of background on the IMI, or Innovative Medicines Initiative, generally. This is a big private-public partnership based in the EU, and the idea is that the EU taxpayers, the European Union fund, and that contribution is matched by contributions in kind from FPA, which is the EU Federation of Pharmaceutical Industries. And there are various topics and focus areas for that IMI, efficacy, safety, training, and so on. And one of them is knowledge management, which is the one that DDMore is mostly based on. And the idea is that through this joint funding between EU and industry, they would aim to address some of the big topics and big issues in industry and in getting medicines to patients. DDMore came out of that, and it's a 5-year project. Our budget was 23 million euros. There were 26 partners. We started in March 2011. And we got a half-year extension, which will lead us up to August 2016. So in just a couple of months, the IMI DDMore project will finish, and we'll talk a little bit more about what will happen after that project finishes. But we want to have a look at some of the products that have come out of this 5-year project. The partners involved are most of the major FPA companies, most of the major pharma companies in Europe. Large amount of contribution from academia, including Leiden, Uppsala, University of Nevada, INRIA, and INSERM in France, Pavia University, and various others. And also SMEs, small to medium enterprises. These are companies that work in the area and provide some support and resource in terms of actually building stuff, building some of these projects and products. The idea being that their work is paid for by the project, and they benefit through being funded to develop tools which they can then use in the future and going forward. And so the vision of DDMore was to improve the quality, efficiency, and cost effectiveness of model-informed drug discovery and development, which we now call MID3, and therapeutic use of compounds. We try to achieve that through a number of products. This is our tube map of the different products that we've developed. The interoperability framework aims to be a hub in which analysts build models and then pass them off between bits of software. Another key aspect is the model repository, where models that have been built can be stored in a kind of pre-competitive space. These are disease models, drug models. The idea being then that the models that get published in literature can be reproducible, downloaded, reused, and taken forward. And so people can build on the knowledge that's already there rather than starting from scratch each time. We achieve this largely through exchange standards, and we have a number of those that we'll talk about today. Workflow looks at how the model building process works and tries to capture provenance of outputs from modeling. We'll not talk about that so much today, but this is something that I think has quite a lot of scope in terms of ensuring reproducible research, ensuring the final products, the reports that we build. You can track back through the model building process and see where all of the content that goes into that report has come from. DDMore has supported development of new tools, and the ISOP webinar has featured some of the projects that have come out of the DDMore funding from Licksoft, but also new diagnostic tools and so on, developed by groups like Uppsala. Another big aspect of DDMore is in the training aspect, and there we have several courses, including one next week on oncology in Pavia. And those courses are aimed at plugging the gap in expertise in modeling and to bring forward the next generation of modelers. Clearly, we're providing support for the products that we develop. Another aspect that might be of interest is the model certification, and this is for models that are in the repository. Certification provides a quality stamp that the model that's there is reproducible and that we can reproduce content from the manuscripts that are with them. So the lines here show how all of these different products join together and how they're related and how you can get from, how you get from interoperability. It uses exchange standards and those are supported and so on. So in terms of what have we delivered up to date, you can see from this slide that we've had public releases of many of these products with a final release aimed at the end of the project. For workflow, the idea is that we would have a kind of proof of concept delivered, and we did that just before Page. And so workflow is kind of behind some of the other projects, but we still aim to have something that's usable and useful to the community by the end of the project. Now, the other thing to point out here is the DDMore Foundation, and that's what's going to come after the end of August, once the IMI project finishes. And in this next slide, we're looking at what is the foundation. Well, where IMI projects are limited to European-based companies and institutions, the foundation is not limited to Europe. So anyone in the world can contribute, anyone in the world can join the foundation and get engaged with the products that were developed in the IMI project. And it's not also limited to those previously engaged with the IMI project. So new partners can come in and new people can contribute to that. And clearly, if we're going to make the foundation work, we need increased engagement, contributions, both in kind, but also in capital and money terms. And we want to capitalize on all of the work that's been done in the IMI project and take it forward. And if you're interested in that, I encourage you to get in touch with Peter Milligan, who's leading up that foundation work. So within the DDMore project, we've got various places that you can engage with what we're doing. There's a DDMore website. There's the DDMore repository, which we'll show. There are, we're present at the Page meeting to discuss what we've delivered and to do a workshop that today's presentation is kind of based on. We'll also be at the ACOP meeting in Seattle. And we have a newsletter, a PDF newsletter, and an online newsletter, which you can see and download. And I will put links to all of these things at the end of the YouTube comments. And here is the group of people who are involved in DDMore. And if you're familiar with some of the folks in the European world of modeling and simulation, I'm sure many of these faces will be familiar to you. For example, here's Mark Lavielle, who gave a previous ISOP webinar on MLXR. So today's presentation will look primarily at the model repository, and we'll look at the interoperability framework and our exchange standards. I'm not going to talk so much on the other aspects, although we'll touch on some of them as we go. So having a look firstly at the model repository and its certification, the idea is that this is the model repository has been developed to enable access to curated and shared knowledge. So these are models where there's a standard for submission. We try to ensure reproducibility. We encourage people to upload sufficient information for those models to be reused. And I think that's one of the key things here, that it's not enough just to put up the existing model and it's not a dumping ground. It's designed so that you actually follow the plan and can show that you can reproduce results that have already been shown. It's a large library of models covering a variety of therapeutic areas, diabetes, oncology, neurodegenerative diseases, infectious diseases, and safety, and other areas. And if you look at the different distribution of how those look, most of the models are either in diabetes or oncology at the minute, some anti-infectives, and so far we have something of the order of 70 to 80 models in the repository. But hopefully more will come over time as we build that model repository up. So what kinds of models do we put there? Well, we'll go on and explain a bit about the model description language and PharmaML in just a second, but you can also put original code. And the idea here, again, is that you upload your model, an example data set, simulated data if it's human data that the model's based on, to avoid any problems of confidentiality of data. But then that allows anyone else to download that model, to run it with that simulated data, and to check that it gives reproducible results. So how do I access the model? Well, it's repository.ddmore.eu, and then what you'll see is this home screen here. So if I just jump to that, so when you first come to the repository, you see this page, and here it gives some background to what you'll see in the repository. One way of looking into the repository is just to hit the Browse tab, and from there you should see a selection of models. If my internet connection speeds up a bit. Or alternatively, you can put in a search term into the search tab here. Okay, that appears to be being a bit slow today. Okay, let me just come back to my slideshow then, and I can show you here. So what you would see is that you would see the model title. You would see that it's in PharmaML. You can see a related publication, if there is one, who contributed that model, and some information about the scope of use of the model, what's in the model, how the model looks. And then in the Files tab, you would see the files associated with that model. Now, we would like each of the models to be uploaded in the PharmaML format, which is our markup language describing the models, and that's the form of the model that should be interoperable between software. You'll see here the associated data, the model description language, MDL file, but also the original model file in non-mem control stream format. And so here, as I've said, if the data is human data, we would like you to upload simulated data. But if it's non-human, then of course you could upload the real data. And the executable, we want to know whether this MDL file has actually been run within the interoperability framework. And if it has, then you can label it as executable.mdl. Okay. So the model qualification procedure then is an added layer on top of submission to the repository, where it's designed to check that that model does what you've said it does, that it can be executed within the interoperability framework. There's a peer review of the model itself and checks against the stated results that are associated with it. And so you can request that certification. Your model has to be publicly available in the repository. It has to meet certain eligibility criteria. And as I've said, there's qualified experts within the consortium, within the foundation, who will evaluate the technical validity and either grant or reject the certification. And the idea here is that there's nothing stopping anyone from uploading a model to the model repository. But once it's in the repository, certification gives an added seal of quality to any of the given models. And the idea then would be that you can trust those models when you download them because you know that they've been checked and peer reviewed. Okay, so the next thing to have a look at is the interoperability framework. Here in this graphic, we're looking at the user. Here it sits over here with the computer. And we've just looked at the model repository. So the idea is that the user goes off to the repository, browses, looks for the models that they're interested in, downloads MDL files that they want to use, and then loads them up into the MDL Integrated Development Environment, or MDL IDE. And this includes an R console for us to actually run software and run estimation. And we'll look at that in a second. When you do some work, when you do estimation or simulation with that model, the model gets converted to FarmML, and then it comes into this converter suite, this framework integration service, task execution service. And what happens is that that FarmML gets translated to whatever target software you want to use via connectors and converters. It then is run in that target software, and the output from that target software gets converted back into a standardized format and passed back to the user. Now, for most people, the stuff that happens in here behind the scenes in this green box is going to be behind the scenes. It's not something that you really want to interact with and have to deal with on most days. But the good news is that when you're working within the MDL IDE, this stuff is hidden away, but the outputs and the conversions that you see here in the target software will be available to you. So that if you want to estimate with Monolix, the conversion will happen. You'll see the MLX-tran file. You'll see the Monolix project file. It'll open up Monolix, it'll run, it'll estimate parameters, it'll bring back the standard outputs from Monolix. And if you want to recreate that later, then that MLX tran and Monolix project file will always be available to you so that you can open up in Monolix. And similarly for non-mem and other tools there. But the idea is that from the user perspective, we kind of hide away an awful lot of this conversion and so on. And so really what the user cares about is the model that they're working on today, and also this return standard output object, which you can do more work with, extract values from, and do your diagnostics, pass it to as final parameter estimates to the parameter object to update values and go on and do some more work. So the idea is to have an integrated workflow where there's a seamless script that goes from start to finish, and everything is updated via functions in R through your R script, and you don't need to keep recoding the model or jumping out and opening up new pieces of software. So the IDE, the Integrated Development Environment for MDL, allows you to look at the MDL code. It has the R console for doing work with that model. You can write scripts in R, and we'll show this in a second. There's a file browser for looking at your models and your scripts. And generally speaking, it's where you do your work. So one of the big questions that may come when you're working or looking at this might be, why do we need another language for describing models? Because we have MLXtran, we have NMTran, we have bugs, we have any number of other tools for describing models. Well, the way that I like to think of it is like this. So this is a score for Mozart's Grand Partita. And it's Mozart's own hand. He wrote this himself. And this is his score for conducting the Grand Partita. And really, it's really just for him to, as an aide-memoire when he's conducting. So if you know music, you can look at that and you can kind of work out what's going on. But there may be some dynamic markings missing. There may be some information that Mozart was thinking of that he didn't need to write in this score because he was working with this music and he knew how it would need to go. It's just, this is his aide-memoire for composing. But nowadays, when you get that score, this is what you see, because a standard has emerged for describing music. And right across the world, anyone can pick up this score, any musician can look at this and know exactly how this should be played. It doesn't take away from the artistic element of actually playing it, but it harmonizes how people look at and how they interpret this music. And I would say that most of the time when we build models, we think of them like this. We build models, we don't really annotate them very well. There's very few standards, there may be some conventions, but generally speaking, it's for each analyst to look at their model, understand it, and work out what it means. What we would like to move to is something like this for models, where it's clear, obvious, unambiguous to anyone that picks up that model, what's intended, how it's intended to be used. The annotations are there, and anyone can replay that model at a future date. So MDL is designed to be human readable, human writable. It's designed to be a standard for describing pharmacometrics models and tasks, to have consistent description of models regardless of what the target tool is that you're intending to use for your work. It's also intended as a standard for communication. So when I hand my model over to someone else, MDL hopefully will make it really unambiguous what it was I was doing, how my model works, how it's parameterized, what distributions are involved. They won't need to know about any tricks or any target-specific information when they interpret that model. The other big thing is that it's intended to be modular. So although we define it in a single text file, in a .mdl file, the idea is that you can pick up and use the pieces of MDL that you need for a specific tool. MDL has 7 main objects. There's the data object that describes the source of the data, how data columns map and how they should be used to elements in the model. It describes the design object for use in optimal design and for simulation, and that can substitute in for the data object. It provides the parameter object, which either fixes or provides initial values for structural and variability parameters. The parameter object can be updated to hold the final estimates of structural and variability parameters. There's also the prior object that provides prior distributions and values for parameters, structural and variability. And then the core element is this model object. Now this defines the structural and statistical equations based on those data input variables and parameters to define how to get from those inputs to the predictions, the parameters, the variables that are required to describe the outputs. And then task properties provides some of the additional information to each target tool to say how to do a specific task. So if you're estimating with non-mem, you want to know about the algorithm that's used and settings that you might have on the dollar estimate line of NMTran. For Monlix, it might be, again, the estimation method here is usually SAEM, but estimation method, algorithm, and then settings to do with that tweaking of the SEM properties. And then the modeling object group pulls together which of those 7 elements are required for a specific task and validates that all of those, the appropriate information is passed between data, parameter, into the model object. And so it kind of defines the collection of items that are required to do work. So the structure here generally, there's a .mdl file which has a model object group, which we call the MOG, which defines the model, and then data or design, parameter or prior, and task properties. And it can have more than one data or design object, more than one parameter or prior object, more than one task properties. But generally speaking, it will only have one model object. And then the idea is that you would pick up that MDL file and then combine the elements that you need on the fly to do the task that you want to do. So for example, when you're doing estimation, you'll probably have data, initial values for your parameters, the model, and then perhaps, say, a Monolix task properties. If you're doing Bayesian estimation, the data may stay the same and the model may stay the same, but instead of parameters, you provide prior definitions for the population and variability parameters. If you're doing VPC, you might have the data structure, you might have final parameter estimates from your estimation step. The model remains the same, but now you're using non-mem task properties. If you're doing prediction, then instead of data, you substitute in design. You might still have final parameters, but again, model stays the same. And then finally, for optimal design, you would have design again, but you might have PFIM or POPED task properties rather than the simulation task properties. So MDL is slightly different from other languages in that it describes what the model does rather than how. Many other languages describe the kind of mechanics of getting from the model inputs to the outcomes, but MDL tries to keep those mechanics out of the model description. And we're trying to keep the model as much as possible independent from the data. Now that means that MDL is perhaps more wordy than other languages, but it means that MDL is more explicit in the distributions that are used, in the correlations, how to define correlations and so on. Because the idea then is that any model that we describe in MDL should be completely described in the FarmML and so translatable onto any target language. Now, to help illustrate how to write MDL, we have a user guide, but we also have a number of use cases. And these use cases cover a variety of different models and model features. We've built them around the warfarin POP-PK analysis as the kind of core of each use case, because the model there is fairly straightforward. There are very few difficult aspects to the model, and it allows us to then look at different features and build them in piece by piece without getting wrapped up in different structural models and different complexity there. But then we also have examples of Poisson models, categorical models, binary models, time to event. Some of these in purple have valid MDL, but we haven't yet completed the process of conversion onto all the target software. But that hopefully will come, if not by the end of the project in August, then within the lifetime of the foundation. But it gives a flavor of some of the areas and the scope for MDL in describing different use cases. We also hope to have examples here. So the standard example models that ship with monoliths, with non-mem, with bugs, encoded in MDL, so that you can see how those models relate to known examples from each tool. And as I said, the user guide is online here at ddmore.eu. And we have the next revision of that coming very soon, which will give the user guide for the latest MDL that's employed in our download. So back to the ddmore platform, this is us, the user. We're writing an MDL. It's getting translated to PharmaML. Work is being done, and it goes on to through the interoperability framework. It runs in different software. So really, my aim now is to try and actually show you how that's working. And so here's an example. This is our interoperability framework. It's, as I said, it was an Eclipse-based system. We have here a model which is for Simeone tumor growth inhibition, and an example that we worked up for PAGE. What you're seeing here, this is the MDL for this model. So the first thing that we see is the data object, and you can see that we describe the columns in the data and how each of those is used within the model. And we map between data columns and variables that are used within the model. So Y here is the response variable within the model. And so we're showing how DV column within the data maps to that response column, and also how the amount goes into the Q1 variable within the model, which is a dosing variable. We have a design object here, which will look at for evaluation, that describes how the interventions are defined. So here we have two arms, a treated and a control arm. We can define how those are, the sampling schedules are set up for each of those arms. For tumor growth here, the treatment starts on day 8 once the tumor has grown a bit, and then these sample times are relative to day 8. So that would be day 8 here, and then 12, and so on. And so what we're measuring here is the tumor size, tumor weight across time, and how that is inhibited by the treated arm. Within the parameter object here, when we're doing estimation, this will give us the initial values for our parameters. You'll see that some of them are fixed, and for some of them there's a lower bound. And when we're doing Bayesian estimation, we need to give priors. And so here we have parameters that feed into the prior distributions. And we also have values here for the parameters that are fixed. So here's the prior distributions for each of those population parameters. And we're using normal distributions for each of those, or in fact, log normal distributions for each of those. And a gamma distribution for the residual error or precision for bugs. And to get the CV, we take the square root of the inverse of that. So here's the actual model itself. We define what the independent variable is. We define variability levels. So here there's only one level of variability. Within the Simeone model and the experiment that's done with it, generally speaking, we have 6 mice on each arm. The tumor weights are calculated at various time points, and then they're averaged to kind of give a naive pool estimate. So that's why here we're not seeing any individual level variability, there's only the observation level. Of course, we could easily extend this model by saying that there's an ID level or a parameter level of variability. But the idea here is that we can stack up however many layers of variability we need. So here DV is level 1, you could have occasion as level 2, you could have ID as level 3, and so on. And so it's very easy then to specify how parameters vary by the different levels of hierarchy. We declare the structural and variability parameters within the model so that those then combine with the parameter object that we've defined. And here we have definition of the individual variables. Now this warning says that for monoliths, generally speaking, explicit definition of individual parameters isn't supported. In this case, because it's just a straightforward assignment of the population value, which is a constant, into the parameter. This works for monoliths, but in general, if you just wrote out an arbitrary equation here, that would cause problems in translation to monoliths. So in the user guide, you'll see how there is certain constructs that are more favorable for interoperability. In this simple example, it works, but I'd encourage you to look at the user guide for more information there. So here's the main piece of the model. It's the model prediction. We specify the differential equations. So here you can see the derivative value, its initial value, and so on. We define the random variable for residual, which is a normal, mean 0, variance 1. And saying level equals dv means that for each dv, we generate a new value of this epsilon random variable. And then in the observation, we say y is proportional error, has a proportional error structure, and the proportional multiplier for the epsilon is CV, and the prediction that we use there is W taught. The next section is just lots of task objects for the different tools that we want to use and the different tasks that we want to perform. Here, these are very sparse. The idea is, though, that we are extending this to allow more target settings so that you can pass target-specific settings over to whatever software you're wanting to use. So that's the model. And what I'm showing in this pane is an R script that works with that model. And so the idea here is that this script then provides a workflow for working with that model and doing tasks. We have, so you've got the whole power of R here. We've provided a ddmore package, which has a number of helpful functions for working with MDL files that we'll look into in a second. But the idea is that it helps you read and write MDL files, translate from MDL to FarmML. It helps you it has functions for estimating using your MDL file. And the idea there is that behind the scenes, the R package is doing conversions and passing jobs to the framework integration service and task execution service to do the work. And we'll see that running in just a second. Here, let me just do some configuration stuff and point to the model file that we're wanting to use and the data file that we're wanting to use. Now, the first thing is to go to that MDL file that I've just defined and then extract the various components. So like get model objects retrieves the MDL objects for the model and then creates an R object containing those elements. So if you look at the MDL object here, those elements correspond to lines of MDL, but they're now as R objects. So we have, what it does is to return from get model objects, interrogates that file and returns a list of however many objects there are of that type. So that's why I've got this square brackets 1 here. Read data object. Remember that my data object is just the R representation of the MDL. So read data object then creates a data frame. And so using the head function within R, we can look at the first few lines of that. And then we can produce our kind of standard exploratory analysis that you might want to do of your data. So here's the tumor growth data. You can see here that there's a treated arm where the tumor growth is inhibited for a number of days and then starts to grow again, and the control arm where the tumor size just increases straight away. So to define the elements required for estimation, if you remember, I said you need to create a model object group. And here I'm specifying that I want to pick up my data object, parameter object, my model object, and then the task properties that relate to Monolix. Because the next step would be to run Monolix and perform parameter estimation. I write that model object group out to file. And you can see here that then I have this _MLX version of the file. I can then perform estimation using that model file. Now, if you remember back to the earlier presentation, what's happening behind the scenes is that we're having conversion to PharmaML. We're running estimation with Monolix, and then it brings the results back from Monolix, converts them to a standardized format, a standard output format, which then gets read back into R objects. So as that's running, you can see some dots there. And when that's running, it creates a Monolix folder. And in that Monolix folder, this is one that I've run previously, but you'll see that it's got the output there. And in this folder, you'll see that there's the MLX_tran file, the project file. And so, as I said, this is a way of getting in, looking and seeing that that translation has worked as you would have expected it. But also this is something that you could open up completely separately from the DDMore integrated development environment. Okay. So while that's running, I'll just pause for a second and check to see if there are any questions online. So VJ is asking, is there an API that can be used to access the model repository? So at the minute, the answer is no. Basically, access the model repository directly from a website interface. It's my hope that before the end of the project, one of the things that we could do is to have R functions that would, instead of pointing to local MDL files, would go to the repository and extract the relevant files directly from the repository. And that would allow you then to start from a position of actually accessing models directly in situ on the repository. Another question is, what's still within industry? The answer is, well, at the minute, this is still a kind of pilot, and although there's been a public beta release in December, and we're aiming for another public release before the end of July. Generally speaking, the use within industry is just as a kind of beta test and an investigative, see how this works kind of testing. I'm hoping that it will become a standard that people will use. But so far, it's still a kind of just an early days look at how this could be used rather than using it in anger. So here, there's another DDMore R package function called get population parameters that runs off to the output of that Monolix estimation and returns back parameter estimates. And we can extract things like the MLE estimates. We can look at what those look like. Now, because the output from this tool is now in a standardized format, one of the things that we can do is we can run the function here as.xpdb that would take that standard output and conform it into the expose format so that we can then pass on to expose. And so you get plots like this for each ID. Here's the fit of that model to the observed data. So this is expose after having used Monolix. Now that may not be a big deal to most because Monolix provides its own diagnostic plots. But the nice thing there is that if you wanted to then produce a report with diagnostic plots in it, it wouldn't really matter what software tool you'd use to perform that estimation. You would have consistent looking plots, consistent looking outputs, regardless of which tool you've used. So I can perform that same estimation with non-mem and do exactly the same steps with non-mem. And note there that I've not done anything around manipulating the actual model. I've just swapped the task properties. Instead of task properties underscore MLX, it's now task properties object underscore NM. And so again, passing from one tool to another, I leave my model alone and I can do yet more work with it. I can do exactly the same thing with bugs here. Again, changing from parameter object to prior object and picking up the bugs task properties. I could run this model using bugs. I'm not going to do that today because it takes some time to do. But here, you could then do things like you could compare between the bugs estimates, non-mem estimates, Monolix estimates. What I did previously was I ran knitr using that R script and produced this HTML file. And so here, basically running exactly the same R script that you're looking at, I created this HTML output with all of the outputs that we're looking at on the screen there. And so here you can see the exposed diagnostics for non-mem rather than Monolix, the estimation with bugs. And with bugs, we use the CODA package within R to then get at the mean values, posterior values for each of the parameter and quantiles for each of those variables. And standard MCMC diagnostics for my model fits. So then you can do things like compare across models and see how these model parameters vary depending on the inputs. When you've got, again, here you can run a VPC of the model. We use PSN here to do this, and we're converting to non-mem first, then using the standard VPC function within PSN. One of the things to see here is the VPC options, where I'm providing a text string with all the standard VPC options that you might want to use. The good thing about this is that then you can specify, you can tailor what happens in the VPC according to your situation. Now the VPC for this plot, because it's naive pooled, is not very informative, but just to show that you can run a VPC based on that. Now, the next step is using Simulix. And here what we do is we convert the MDL file that we have here using the non-mem MDL file. We convert that to FarmML because Simulix can use a FarmML model as the description of the model. I create the population parameters, the dose administration times, what to sample or what to observe, define the groups, and then call Simulix with those inputs, and I can plot them just as you would normally with Simulix. Now, one of the things that you'll notice here is that I'm specifying the parameters, and the design elements in R. But one of the things that I'm working on is an as.simulix function that would take, if you recall from the MDL IDE, it would take these design elements that are specified in the design object and essentially pass them forward into Simulix so that you wouldn't need to re-specify what those were. In other words, it would take the R object for that design and pass that and work out the correct inputs for Simulix. And this, I think, is one of the beauties of what we're dealing with here, because all of these elements are in R, they can be manipulated using R, and you end with a number of emerging tools in R. So like MLXR that's been discussed at ISOP, Ron Kaiser's PKPD Sim, MRG Solve, RxODE, any number of these emerging tools within R. You could take the MDL representation within R and conform it into the right inputs for each of those tools. So really it would then be MDL as the hub for future kind of interoperability with other tools. We also integrate with PFIM, and again, here we're converting. First, we're taking the parameter estimates from the non-mem estimation and updating the population parameters. That's what the update par object function does. And then creating a new model object group for PFIM and calling PFIM here with this function. Some tools are less advanced in integration than others, but ultimately we would aim to have an R function for the ddmore package called something like optimize or evaluate here. And here's the PFIM output for that model. You can see how the model has been converted into the right inputs for PFIM, the model description, and also the design elements have been picked up from the design object. And you've then got the appropriate outputs to have a look at from the PFIM evaluate option. Similarly, for PopEd, we take the MDL file and we convert we say as.poped, and then the great thing is that we're just using PopEd as you would normally. So this is another optimal designs package with R. And again, the beauty there is that I'm not having to reinvent functions that already exist in other packages. I'm just preparing the inputs that we have for use with that package. And you can see here that there's the appropriate outputs from PopEd. So lastly, if I come down to show the structure here. So this is the R object for my model. And you can see here in the model prediction block, so this is an S4 object in R. And these, the slots in the R object correspond to the blocks in R. So there's a block in the MDL called model prediction. And then there's a sub block called DEQ. And here you can see that there's the different elements here. So there's an equation definition, and on the left-hand side there's a variable called wtot, and then it's a character string for how that is made up. Similarly, you can see here that there's a derivative. Here's the equation for that derivative, and here's the initial value for that derivative. So again, it shouldn't be difficult at all to take that R object and create, as.pkpdsim, as.mrgsolve to give the appropriate, or as.desolve to give the appropriate inputs for any other software tool that we're interested in. Okay. quickly then, to sum up, to have a look at the exchange standards. FarmML is the main one that's the machine readable or machine translatable form of the model. We talked about the standard output format. This is also a markup language format describing the standardized conformed way of describing the outputs from each estimation tool. Another piece of work that's been done is categorizing and describing probability distributions and how those relate to each other. How all of these tools come together. You've got FarmML here describing the model. This gets translated to whatever tool you want to use to do the pharmacometrics work. And then the outputs of that get conformed to the SO. FarmML is readable if you understand markup languages. But generally speaking, what we're saying is that the MDL is the kind of human readable from end to FarmML. And for each task, you may have a different FarmML representation of that, because then you're combining the model object group elements into the relevant inputs for the next step in your workflow. For Probonto, what has been done is to characterize the many different probability distributions and how those interrelate. So how different parameterizations relate to each other. There's many parameterizations for log normal, but also how you get from log normal and how those use or are related to other distributions. So the idea here is that having described interrelationships between each of these things, it's then possible within FarmML to refer to them, and then in the conversion know how to get from one version or one parameterization of that distribution to another. For example, in the Poisson, you've got distributions like zero inflated Poisson, generalized Poisson, double Poisson, Conway-Maxwell Poisson that are related to the Poisson. So in other words, you can set parameters to zero or fix them to give you a Poisson. But then Poisson can be approximated by a normal one distribution. And as I've said, different parameterizations of the log normal are used in different tools. Probonto allows us to quickly and easily see how those are interrelated and which tools use different variants and different types of log normal distribution. So at Page this year, we presented what we've just shown you, and we were using the Simeoni model. And so at Page, myself on the right here, and Stuart Moody, who developed the MDL and MDL IDE for us, met Monica Simeoni, who developed that model. So it was quite a momentous moment for us as we met the person responsible for the model that we've been working with. And with that, I'll wrap up this webinar. I'm happy to receive comments and questions after the presentation via YouTube. I thanks for your attention, and hope to see you at future ISOP webinars. Thank you.